Dr. S. Nagan. He is an associate professor in civil engineering at Tyagarajar College of Engineering, Madurai. He pursued his undergraduate and postgraduate studies from Tyagarajar College of Engineering and completed his PhD at the Madurai Kamarajar University. He has more than 20 years of teaching and research experience. He has worked in many prestigious institutions including PSNA, College of Engineering and Technology, Dindigul. He has published more than 25 research papers and 5 books under his name. Apart from all this, he is a life member at the International Society for Environmental Protection and also at the Indian Society for Technical Education. To add to all of this, he is won the Best Staff Advisor at the ISTE Students Chapter.
Welcome to UGC lecture series for Bachelor of Architecture. In this session, we will be continuing the bending and shear stresses. In the earlier lecture, we have seen computing the bending stress for rectangular section. We have taken a simply supported beam and we have seen how to compute the bending stress at the top fiber and bottom fiber. Now, as a continuation, we will see an example of an I section. So, we will be calculating bending stress for an I section. So, this is the example that we need to compute the bending stresses for the I section shown in figure. I will draw the section, and then it is subjected to a bending moment of 300 Newton meter. We need to also plot the bending stress distribution. So, the top flange is 60 mm by 10 mm. We have the top flange 60 mm by 10 mm. So, this is an I section, bottom flange is 40 mm by 10 mm. So, it is an unsymmetrical I section like this. So, the top flange is 60 mm, always the first dimension will be horizontal dimension followed by the vertical dimension. So, vertical dimension is 10 mm, then web is of 10 mm by 30 mm. So, 10 denotes the width, always first dimension will be the width or horizontal dimension and second dimension will be the depth 30 mm. And then the bottom flange is of dimension 40 mm by 10 mm. The problem is to compute the bending stresses for the unsymmetrical I section. We have been given bending moment value of 300 Newton meter. So, we will have to compute the bending stress at various levels. We have the bending equation as F equal to m by I into y. M is given as 300 as the bending moment 300 Newton meter. So, 300 into 10 power 3 Newton millimeters. We always want to have consistent set of units. So, it need to be in Newton millimeter, then only we will be getting the bending stress as Newton per millimeter squared. Suppose the bending moment value is not given, we know how to compute the bending moment for different loading case. So, the first thing is to compute the maximum bending moment if it is not given like this, and then we need to compute the moment of inertia m divided by I into y, we need I value. So, before computing I, the center of gravity need to be calculated using the formula y bar equal to a 1 y 1 plus a 2 y 2 plus a 3 y 3 by a 1 plus a 2 plus a 3. So, you have the section like this, the unsymmetrical I section. As a first step, you mark the individual dimensions of the elements, say number 1, 2, 3. So, the element 1 will have a dimension of 60 mm by 10 mm. So, mark the dimension as 60 mm by 10 mm and the web having a depth of 30 mm by 30 mm is the depth and width is 10 mm and the bottom flange having dimension 40 mm by 10 mm. So, this is 40 mm and this is 10 mm. So, area of element 1 here is given by 60 mm into 10 mm 600 millimeter squared. Then y 1 is equal to distance of CG of element 1 from the top. So, from the top we can compute y 1 like this. So, this is actually y 1. So, y 1 will be equal to 10 divided by 2 as mentioned here, 10 divided by 2 equal to 5 mm, and then A 2 will be equal to area of the element 2. So, the width is 10 mm and the depth is 30 mm. So, 10 into 30 300 millimeter squared. So, A 2 is equal to 300 millimeter squared, and y 2 equal to distance of CG of element 2 from the top. So, from the top if we take, we already have 10 mm here, and then the element 2 will have CG of say 30 divided by 2. So, 10 plus 30 by 2 equal to 25 mm, 15 plus 10 25 mm. Then A 3 area of cross section of element 3, which is equal to 40 into 10, which is equal to 400 millimeter squared, and y 3 is the distance from the top, the reference axis for y bar to the CG of element 3. So, that will be equal to, we have a depth of 10 mm for the top flange plus 30 mm for the web. So, 10 plus 30 and CG of element 3 will be at a distance of 10 by 2. So, 10 plus 30 plus 10 by 2 will be equal to 45 mm from the top. This is the y 3 value. So, we mark y 3 here, y 2 is this and y 3 is this, y 3. So, y 1, y 2, y 3 values are marked. So, once a 1, y 1, a 2, y 2 and a 3, y 3 are known, we can easily compute the y bar value. So, y bar value is equal to 21.92 mm from top. So, for this section, for the unsymmetrical I section, the first and foremost thing is to compute the CG distance, and we have calculated the CG distance from the top as 21.92 millimeters, and this shall be considered as y t, that is the extreme fiber distance up to the top fiber. So, we can easily calculate the extreme fiber distance up to the bottom fiber y b using the formula. We have overall depth d, we have overall depth as 50 mm. So, 50 mm minus 21.92, that is y t, will give you the value of y b. So, y b is computed as 28.08 millimeters, 28.08 millimeters. Then moment of inertia shall be calculated using the formula. Say we have divided into 3 elements, we have divided into 3 elements. So, for element 1 I self plus area into distance squared, for element 2 I self plus area into distance squared, and for element 3 I self plus area into distance squared. So, self moment of inertia will be b d cube by 12. So, accordingly I equal to b 1 d 1 cube by 12 plus b 1 d 1 into y bar minus y 1 whole squared plus b 2 d 2 cube by 12 plus b 2 d 2 into y bar minus y 2 whole squared plus b 3 d 3 cube by 12 plus b 3 d 3 into y bar minus y 3 whole squared. And we very well know why we get y bar minus y 1, y bar minus y 2 etc., because that is the distance between the centroidal x axis and the CG of respective elements. So, if I am interested in element 1, then y bar minus y 1 will give me the distance between the neutral axis and the centroid of element 1. Similarly, y bar minus y 2 will give the distance between the neutral axis and the CG of element 2. And similarly, y bar minus y 3 will give the distance between the neutral axis and the CG of element 3. So, substituting these values, we have b 1 d 1. So, b 1 always refer to horizontal dimension, d 1 refers to vertical dimension. Similarly, b 2 means the width of web and d 2 is depth of web, and b 3 is width of bottom flange and d 3 is depth of bottom flange. So, substituting these values, we will get moment of inertia I as 4.185 into 10 power 5 millimeter power 4. So, we have values of bending moment m, we have computed the values of moment of inertia I, we know the values of y t and y b. So, substituting the values of m, I and y t and y b, we get stress of 15.71 Newton per mm squared at the top fiber and 20.13 Newton per mm squared tensile at the bottom fiber. So, we know that simply supported beam subjected to any loading, in case of simply supported beam, the bottom fibers will be subjected to tension, and above neutral axis will be, or centroidal axis, we will be having compressive stresses. So, the bending stress distribution will be as shown in figure. Say we need to plot the bending moment distribution for the I section. So, first mark the centroidal axis, mark the top fiber, bottom fiber, draw a reference line, top fiber subjected to compressive stress of 15.71. So, 15.71 mark to the right side of the reference line. So, we have 15.71 Newton per mm squared compression, and bottom we have 20.13 Newton per mm squared. So, that is tensile. So, I will mark like this and connect these two, we will be getting top as compressive stress and bottom as tensile stress, the value being equal to 20.13 Newton per mm squared. This is the bending stress distribution across the depth of the beam for the unsymmetrical I section which we have been given. Next example is, we have been given a cantilever beam of span 2.5 meters and it has T section of flange 100 mm by 25 mm and web of size 15 mm by 125 mm. It is subjected to a point load of 1.6 kN at its free end. We need to compute the bending stresses. So, the bending stress equation is given by F is equal to m by I into y, m is equal to maximum bending moment. So, we have been given a cantilever beam, subjected to a point load of 1.6 kilonewton, 1.6 kilonewton at its free end. So, the span is 2.5 meters. So, as a first step we will compute the maximum bending moment. So, maximum bending moment will occur at the fixed end and its value will be equal to load into distance, that is 1.6 into 2.5, which will be 4 kilonewton meter, that is to be expressed in Newton millimeters. So, it is equal to 4 into 10 power 6 Newton millimeter. In case if we are given a cantilever beam with UDL, in that case maximum bending moment will be WL squared by 2. Similarly, we may be given uniformly varying load like this. So, whatever may be the given loading and whatever may be the given type of beam, we should be in a position to compute the maximum bending moment using the concept studied in unit 1 on shear force and bending moment. So, one has to be thorough or conversant with finding shear force and bending moment, as well we need to be thorough with computing the moment of inertia, and that means properties of sections before proceeding to bending stress calculations. Then moment of inertia. So, we have T section, we have been given a T section. So, the flange width is 100 mm, flange width is given as 100 mm and the flange thickness or flange depth is given as 25 mm and the web dimension is, we have web is of size 15 mm by 125 mm. So, 15 mm by 125 mm. So, before computing the moment of inertia, first the centroidal distance need to be computed using the formula A1 y1 plus A2 y2 by A1 plus A2 by dividing the given compound section into 2 elements. So, your A1 will be equal to 100 into 25, that is 2500 millimeter squared, and y1 will be equal to the distance from the top to the CG of element 1 marked as shown in figure. So, the value of y1 will be equal to 25 divided by 2, which is equal to 12.5 mm, and the value of A2 will be 15 mm by 125 mm. Therefore, 1875 millimeter squared will be the area of cross section of element 2, and y2 will be the distance from the top to the CG of element 2. So, this distance is y2. So, the value of y2 will be equal to, we have clear dimension of 25 at the top plus 125 divided by 2, because CG of element 2 will lie at 125 by 2 from the flange, then it has to be added to the 25 mm at the top. So, 25 plus 125 by 2 will be 87.5 mm. Therefore, the CG from top is equal to, substituting the values of A1 y1 A2 y2 etc., will be getting the CG from top is 44.64 mm. So, this distance is, this is the T section So, for the T section we have computed the CG distance from top as 44.64 mm, and from the bottom we can compute using the overall depth. The overall depth is 150 mm. So, 150 minus 44.64, which is equal to 105.36 mm from the bottom. So, this distance is considered as YT and this distance is considered as YB. So, we have YT and YB. The next thing to be computed is moment of inertia. So, moment of inertia shall be computed using the formula B1 D1 cube by 12 plus B1 D1 into y bar minus y1 whole squared plus for the second element B2 D2 cube by 12 plus B2 D2 into y bar minus y2 whole squared, and B1 D1 we know. So, this is if we have the T section like this, we have the T section like this, B1 will be this and D1 will be this. Similarly, for the web portion, this is B2 and this is D2. The width of the web is B2 and depth of the web is D2. So, substituting the values, we all have the values y bar y1, y bar y2 etc. So, substituting the values, we will be getting the value of moment of inertia as 8.6 into 10 power 6 millimeter power 4. Now, we can easily compute the value of the bending stresses at the bottom fiber and at the top fiber using the formula m by I into yt and m by I into yb. All these values are known, therefore, we can compute the value of Fb as 49 Newton per mm squared and Ft as 20.76 Newton per mm squared. And we know that in case of cantilever beam, because the given case is a cantilever beam, in case of cantilever beam, the top fibers will be subjected to tensile stress and bottom fibers will be subjected to compressive stress. That is the reverse case of a simply supported beam. In case of simply supported beam, we have bottom tension and top compression, whereas in case of cantilever beams, top tension and bottom compression. This need to be remembered while computing the bending stress, and the bending stress distribution shall be drawn like this. So, the bending stress distribution will be like this. So, you have the T section. So, draw the centroidal axis, extend the top fiber, extend the bottom fiber, draw the reference line. At bottom we have 49 compression. So, mark 49 compression, and at the top we have 20.76 tensile. So, 20.76 Newton per mm squared, which is tensile at the top and at compression at the bottom, value equal to 49 Newton per millimeter squared. So, this is the bending stress distribution. This is the bending stress distribution across the T section. Next, you will see composite beams, because practically we involve composite materials also. Say for example, we may be having a timber beam or timber cross section and it shall be reinforced or it shall be cladded with some steel strips like this. So, this will form a composite material or composite section, that is containing two different materials. So, in that case, how to compute the bending stress, that is the case here. Similarly, we can also have several combination of other materials, like say for in this example a rectangular section timber beam. So, basically a timber beam is there, is 50 mm wide and 75 mm deep. So, the timber beam is 50 mm wide and 75 mm deep. It is clad with steel plate. So, we have provided steel plate at the top and bottom. The steel plate is of thickness 10 mm thickness. We will have to calculate the maximum stress in the steel and timber when a moment of 4 kilonewton meter is applied. The Young's modulus for timber is 10 GPa and for steel is 200 GPa. So, if we are given composite sections like this, the first step is to convert the given section into an equivalent section of same material. We have two different materials like timber and steel. So, the first step is to convert into equivalent, either it can be converted into equivalent timber section as a whole or it shall be converted into equivalent steel section as a whole. So, let us consider an equivalent steel section. So, the steel section will comprise top flange of dimension 50 mm by 10 mm. So, the equivalent section is drawn. So, it can be converted into a equivalent section like this, comprising totally steel. We have replaced timber, formed a equivalent section. So, the top 50 and 10 remains the same. So, the steel plate dimension is 50 mm by 10 mm. Similarly, bottom remains the same 50 mm by 10 mm. Only thing is the web, actually the web is of timber. Now, we are transforming into equivalent section, therefore, the equivalent thickness in terms of steel has to be calculated. So, the equivalent section, the thickness will be computed using the formula. The thickness of equivalent section will be the width B multiplied by E t by E s, where B equal to width of the timber section. So, width of the timber section is 50 mm. So, 50 multiplied by the Young's modulus of timber and Young's modulus of steel are given in the problem. So, using that we can find the equivalent thickness of timber section to we want to transform into a steel is B into Young's modulus of timber divided by Young's modulus of steel. So, that will give us 2.5 mm and hence this section has thickness of 2.5 mm. This is the equivalent section. Now, the equivalent section is a symmetrical I section. We know very well to compute the value of moment of inertia of sections like this. Symmetrical I sections, the moment of inertia is given by B d cube minus B small b d cube by 12, where capital B is this and overall depth is d, and small b will be equal to capital B minus thickness of web. Therefore, small b will be 47.5 mm and small d will be overall depth minus 2 times the thickness of the flange. So, we will be getting capital B, we will be getting capital D, small b, small d are known. We can compute the value of moment of inertia. So, the moment of inertia I is equal to 1.9025 into 10 power 6 millimeter power 4. The stress at layer B, that is at bottom layer of top flange. Say we need to compute the stress at different levels here separately or clearly, because being a composite section we need to arrive clearly. So, let us say consider this layer and this layer. So, stress at layer B, that is at bottom layer of top flange. So, this is layer B and this stress at B is given by F suffix B, which is equal to m divided by I into y 1. This is y 1 and this is y 2. So, y 1 value we very well know as 37.5, because we have 75 mm. So, this will be 37.5 mm. So, y 1 value will be 37.5 mm. The bending moment value m is given as 4 kilonewton meter and hence F b, that is stress at layer B, is m by I into y, which is equal to 78.84 Newton per mm squared. However, this value need to be modified or transformed for equivalent timber section. How can we compute this? We can compute the stress at level B corresponding to timber as F b multiplied by E t by E s. So, you will have the value of E t and E s, substituting you will get the value as 3.942 Newton per mm squared. So, that is the stress at layer B corresponding to the section. Then stress at layer A. So, layer A is the top. So, stress at layer A, that is at the top layer of top flange equal to m by I into y 2. Y 2 we know that it will be equal to 37.5 plus 10 47.5. Therefore, the stress in steel will be 99.87 Newton per millimeter squared. So, this how we should compute for composite sections. So, for composite sections initially transform the section into an equivalent section using the equivalent width computations, using the different moduli of elastic modulus or moduli of materials. Then you compute the values and then again we need to convert the stress corresponding to that particular material using the formula, the stress obtained for equivalent section multiplied by Young's modulus of the material concerned by Young's modulus of the material transformed. So, that will give you the stress at different levels for composite sections. So, with this we conclude that we will be in a position to compute bending stresses for any given section, let it be a symmetrical I section or unsymmetrical I section or a rectangular section or a circular section. We can easily compute the bending stress across the bending stress variation across the cross section or across the depth using the formula m by I equal to f by y. All we need to review or recall is we would be familiar or we should be strong in computing the maximum bending moment in different cases, like bending moment in case of cantilever beam, in case of simply supported beam and in case of overhanging beams. Similarly, we should be in a position to compute the values of moment of inertia by calculating the center of gravity first and then the moment of inertia using parallel axis theorem. So, when these values are able to be calculated, then it becomes easier to compute the bending stress, and then the stress shall be computed and plotted at different levels, say at top or bottom. And the things to be remembered in case of the nature of stress is, in case of cantilever beams, the top section or the section above neutral axis will be subjected to tensile stress and the sections below neutral axis will be compressive stress, whereas in case of simply supported beam, the sections below the neutral axis will be subjected to tensile stress and the sections above neutral axis will be subjected to compressive stresses. That is why we provide tensile reinforcement at the bottom of a rectangular beam or of a simply supported beam, and we provide reinforcement, tensile reinforcement at the top of a cantilever beam. Examples will be, you can take a sunshade. Say sunshade is a cantilever slab. So, in the cantilever slab tension occurs at the top, hence we provide the reinforcement at the top, main reinforcement at the top. In case of simply supported beam, we provide the main reinforcement or tensile reinforcement at the bottom. So, these are the things one need to remember in case of bending stresses, and also we should be clear with the assumptions made in deriving this bending equation, and m by I equal to f by y equal to E by r, that is the equation, and we have not used the part E by r so far, and problems shall also be asked or involved in using the terms. So, in the terms we will be in a position to obtain the radius of curvature of the beam. So, you will be knowing m value, I value, that shall be equal to E by r, or you will be given f value and extreme fiber distance, and that shall be equal to f by y equal to E by r. Using that we can calculate radius of curvature, or sometimes you will be asked to calculate the Young's modulus of the material of the specimen giving the other values. So, the equation should be used to compute the unknown values or the values which are required. So, let us see the questions to be solved with the case which we have studied so far. So, we will sketch the bending stress for the following case, that is, we have been given a cantilever beam loaded like this, and the cross section is of L section, an angle section. So, the loading is 15 kilonewton per meter, the distance is 3 meters, 1.5 meters, and the cross section is an angle section of dimensions 50 mm and this is 100 mm. The thickness is 10 mm. So, you will have to sketch the bending stress across the cross section. Similarly, the another example is we have been given a simply supported beam with 2 point loads of 10 kilonewton and 15 kilonewton, and the cross section is an I section like this. So, this is 1 meter, 1.5 meter, 1.5 meter, and this is 30 mm, 75 mm, this is 25 mm. The thickness of top flange is 15 mm and the width of bottom flange is 60 mm. So, we will have to compute the bending stress in these two cases. Thank you.